Okay, can everybody see the slides and the transition?
Yes.
Okay, great. Okay, so uh, just before we start, again, a reminder, um, our homework 2 will be due in next Tuesday. So if you haven't started yet, please do it as soon as possible. The workload is much less heavier, much less heavy than homework 2, but you still need to spend some time running your algorithm and collect the results, because we want you to evaluate uh, how the error or the estimated generalization vary along with more and more iterations like in boost, eta boost, and bagging. And also we give you some kind of methods to estimate the bias term and the variance term in the expected generalized error. Those are not hard, but it does require you to run enough iterations to get like accurate estimate. Otherwise, you won't say how we do the averaging bagging strategy can indeed reduce the variance and so as to reduce the whole expected generalization error. Okay, so please start doing homework 2 as soon as possible and take advantage of our office hours and Piazza um, discussions. And the second thing is about the setting of the uh, course project. I assume that you should have already decided which type of project you're gonna do, and who is your team member, or you have set up your Kaggle account and successfully submitted some dummy submissions, right? You should start trying. We're gonna release the deadline for the midterm report. I expect everybody should be able to submit a midterm report by the end of March. Okay. So any questions so far about the homework and the project requirement? Okay, sounds great. Um, so today we're going to talk about perceptron algorithm, our first learning algorithm for linear classifiers. Uh, in the last lecture, we talked about learning algorithm for linear regression. Uh, Remember, regression is a different task from classification, right? They differ in the outputs, right? The output labels. For regression, our output labels are continuous, right? We use a linear function to predict the continuous output, right? And the most commonly used approach is called least mean square regression, where we construct a cost function, which is summation of the square error in predicting each training example, right? And then we'll talk about two dominated and very popular optimization algorithms to minimize this mean square loss or cost function, which is called uh, gradient descent and stochastic gradient descent, right? So if you are doing homework right now, you should have already implemented your own gradient descent, stochastic gradient descent. You can look into their behaviors, how they update the model parameters, including the weights and the bias, right? And how they vary along with different parameters. But eventually, they're gonna converge to the same local minimum, because the least mean square error or least mean square cost function is essentially convex, right? Any local minimum is equivalent to the global minimum. So those are all about the learning algorithm for linear regression. But from today, we're going to talk about a few widely used learning algorithms for linear classifier. Right? So we're going to start with the simplest approach. It's called perceptron. However, you see that it can be seen as kind of a grandpa of deep neural nets. And then we'll talk about more robust and more theoretically guaranteed learning algorithm called structure risk minimization, or maximum maximizing margin classifiers. It's called support vector machines. And then we'll talk about the several uh, two approaches, naive-Bayes and logistic regression, which learn a linear classifiers in probabilistic framework. And in the meantime, we'll talk about like how do we extend a linear classifier to nonlinear classification tasks based on the feature mapping trick we showcased previously. This is basically our plan. Right? So we're gonna start with perceptron algorithm. So here's the outline. We'll first introduce the algorithm steps of the perceptron algorithm. You'll see that it's really straightforward. Um, but then we'll talk about why this simple updating rule in the perceptron algorithm makes sense, right? Do we have like what is the rationality behind those updates? Do we have a more intuitive interpretation or illustration in geometry view? And then we'll talk about some theoretical guarantee about perceptron algorithm. It's called perceptron mystic bound. We will discuss like what kind of behaviors a perceptron algorithm uh, will have under different types of data, like for if the data is totally linearly separable, right? And perceptron algorithm, you see that no matter how you fit these training examples to the perceptron algorithm, it always guarantees to find a separating hyperplane that well separates all positive examples from negative examples, right? This is pretty good, right? And what if the data set is not linearly separable, right? Meaning that uh, you're never able to find a separating hyperplane. Then what kind of behavior or perception algorithm um, uh, will be look like? Is you'll see this, it will enter into a infinite loop, right? And finally, based on the standard framework of the perception, we'll introduce a few variants of perception, like what we introduced the variants for the decision tree, right, to improve the robustness, to make it more, um, to make it generalize better than the original perception algorithm. Okay, so here's the outline. So um, let us start with the perception algorithm first, right? So, uh, so first, to introduce the algorithm steps, right, we should be familiar with the formulation of linear classifiers. Right? This is just to recall, right? Just to refresh our memory about definition of linear classifiers. So in general, we assume that our input is an n-dimensional vector x, right? And output is a label, and which takes either -1 or 1. So for convenience, here we assume y is strictly -1 or 1, right? Rather than 0, 1. But of course, you will see later, we can easily transit to the real binary case where y can take 0 or 1. It doesn't matter. And the linear classifiers are also called linear threshold units. So these LTUs, those uh, names are coming from the early development of artificial units, but they are exactly the same thing. So linear thresholds units classify an arbitrary example X using the following classification rule, right? What is our rule, right? We get our prediction or predicted label by taking the sign of a classification function, right? So the classification function is a linear function, which has the same form as used in linear regression. It is W transpose X plus B, right? So W is a feature vector, right? Has the same dimension as the input vector. And then we have a scalar bias parameter, right? So we first calculate this linear classification function, then look at the sign, right? If the classification function is no less than 0, a sign is 1, right? meaning that our prediction is a positive label. Otherwise, if the classification function is negative, the sign is -1, implying that our prediction is a negative label. This is just the definition of linear classifiers. And we have some more nice looking graphical illustration of these linear classifiers, right? We'll see it when we talk about, we'll see it more when we talk about neural networks, right? You'll see that neural networks can be seen as a simple combination and accumulation of such basic units, right? So this unit is called linear threshold units, where each input feature is represented by an input unit. Here, x1 to x8, right? Here we assume n equals to 8. Then we also place a constant unit 1, right? And along with each feature unit is a weight and the bias, right? So W1 is associated with x1, W2, x2, W3, x3 until W8, x8, and a bias parameter associated with constant feature 1, right? And those feature units amplified by the associated weights and bias, and then collected and transported into this intermediate unit. Inside this intermediate unit, they take the summation over the incoming inputs. So basically saying the output of this intermediate unit is a summation over the incoming signals. So those incoming signals are just as W1, X1, W2, X2, W3, X3 until W8, X8 plus B, right? And you add them together, you get output, right? And then the output of intermediate node is fed into this top node. And inside this node, we take the sign operation and use the output of sign function as our prediction. So you can see this is just a graphical illustration of our classification rule, right? How we calculate the inner product between the weight vector and input feature vector plus the bias parameter and take the sum. Okay, any questions so far? I assume everybody is comfortable with this, right? Just to refresh our memory. But if you feel anything like unclear, unsure, uncomfortable, just interrupt me and to clarification. Okay. And also, we'll introduce the linear classifiers. We'll also introduce the geometry view, right? The linear classifiers have a nice geometry view. We can use the classification function to construct a classification boundary, which is represented or described by this equality, right? So this equality is that the classification function is exactly 0. So basically, this classification boundary partitions the whole instance space into 2 half spaces, right? So all the instances in this half space will be classified as positive examples. And all the remaining examples, namely in the other half space, will be classified as negative examples. And in the 2-dimensional space, right, our classification boundary obviously is a line, right? So in the 3-dimensional space, what is our classification boundary?
A plane.
Yes, a plane, right? A plane. And in general, right, we consider like high-dimensional space, like n-dimensional space, our classification boundary is usually referred to as a hyperplane or classification hyperplane, right? And another important property regarding the linear classifier is that we only care about the sign, right? Not the magnitude, meaning that we can steal the model parameters. Like here, they include W1, W2, and bias parameter B, right? By arbitrary constant positive scalar, right? From 0.0001 to 1 billion or 1 trillion, it doesn't change the classifier at all, right? Because from the geometry point of view, right? If you just multiply B W1, W2 by any positive constant, it doesn't change the position or the angle of this classification boundary at all, right? Oh, another thing everyone should keep in mind is that the weight vector here is W1, W2 is always orthogonal to the classification boundary. Right? This is something everybody needs to keep in mind because we're going to use that to explain many behaviors of our linear classifiers and learning details.
I have a question about this.
Uh-huh.
So if we were to take, so let's say that the data is exactly the same, like it would be as the same coordinates in this coordinate system, except that all the positive examples and negative examples switch places.
Uh-huh.
So this linear classifier would still properly classify the data, but because of this convention we use with the classification boundary, we would want to flip the weight vector to now be negative, the negative version of what we have here, because we always want it so that that vector is we want it so that the dot product between our weight vector and our x vector for the positive examples is going to be positive.
Yes.
Okay.
Yeah.
So we would need to account for that. Okay.
Yeah. That's why, as I said, like we can only multiply all those W1, W2 by a positive scalar, right? If you multiply it with a negative scalar, you actually change the property of the classifier. It does matter. It does matter.
Right. Okay. Sounds good. Thank you.
Okay. With this like a formulation and a geometry view of linear classifiers, now let us talk about perceptron. Right? Remember, perceptron is just one learning algorithm for linear classifier. Right? We're going to start with. We'll see quite a few as our classes go on. Right? So here, I just want to start with the history of the perceptron. So perceptron was originally invented by a psychologist. So here is the original paper, right? It was published in a journal in psychology, right? It's called Psychological Review in 1958. This is quite about 70 years ago. Yeah, it's around 70 years ago, right? But at that time, at that time, it was like a baby stage of artificial intelligence. So you can also say many hypes. It's very similar to the hypes today, right? You can say that many kind of like claims, forecasts regarding how artificial intelligence will oversee human intelligence or behaviors like human and replace human beings and all such kind of stuffs, right? So this kind of like a fear or forecast or claims have already been showing up 60 years ago, right? So here I just want to share with one piece of paragraph uh, published in New Yorker in 1958, December 6th, right? I can just briefly read through this graph, right? Having told you about the giant digital computer known as IBM 704, right? If I'm taken not artificial intelligence, if I've taken computer architecture course or similar course before, you will know that this is kind of a classical computer architecture design. And how it has been taught to play a fairly credible game of chess, we'd like to tell you about an even more remarkable machine, the perceptron, which we're going to discuss today, which, as its name implies, is capable of what amounts to original thought. The first perceptron has yet to be built, blah, blah, blah. Right? So, but later we'll see that perceptron has nothing to do with any intelligence. It's just trying to find a separating hyperplane to separate a bunch of positive examples from a bunch of negative examples. That's it. Um, of course, if you have patience, if you're patient enough, you can read through this a piece of article published in New York Times in 1958, right? So sometimes, like if you can give some fancy name, right, magic name to the algorithm or model you invented, it might cause some such kind of hype, right? Okay, so here is a brief summary of the perceptron algorithm. Um, it was originally developed or invented by Rosenblatt in 1958. And the goal, again, has nothing to do with artificial intelligence. It's just to find a separating hyperplane, like to separate data, typically positive examples and negative examples. And we'll see that uh, we have some theorem showing that for separate data, um, the algorithm is guaranteed to find one separating hyperplane. Its nature is an online algorithm. It's pretty similar to the stochastic gradient descent algorithm we introduced in the last lecture. So we feed the data examples or training examples one by one to the perceptron algorithm. So it processes one example at a time, right? And then make updates according to the current prediction results. And you can repeatedly feed the stream of training examples to this perceptron algorithm again and again until it converges or it failed to converge, and it will see that, okay, maybe the data is not linearly separable. And finally, I based upon the standard algorithm framework proposed by Rosenblatt. We have several variants exist, like margin perceptron, like average perceptron, which are mostly used in practice. We're going to discuss briefly towards the end. Okay, any questions so far? Great. So now here is the algorithmic framework of the perceptron algorithm. So again, we assume our input is a sequence of the training examples, right? X1, Y1, X2, Y2, X3, Y3, until say X big N, Y big N, right? So every training example, the input Xi belongs to the n-dimensional input space where the output Yi is either -1 or 1. Right? So here, I want to emphasize that for convenience, right? We assume this Xi has already included the augmented constant feature 1. Right? So remember, when we talk about the representation of the linear classifiers, we talk about like some trick to simplify the notation, right? We do not want to always write down this bus parameter b, right? So we kind of fold this bus parameter b into the weight vector, and correspondingly, we're going to fold or append a constant feature 1 into x, so that in our new weight vector and new feature vector, with our new weight vector and feature vector, we can represent our classification function simply by one inner product, which is W transpose X, right? So remember, W includes a bus parameter B, and X includes a constant feature 1. Right? So in this way, we do not need to explicitly write out this bus parameter B, okay? And then our prediction is just to take the sign of this inner product. So our whole algorithmic framework and analysis, all kinds of stuffs will be based on this simplified notations, right? But please keep in mind that we have embedded this bias parameter and constant feature into W and X respectively. Okay. So we assume that each input, augmented input, belongs to n-dimensional space. That means that, okay, in this n-dimensional space, we have one constant feature 1, right? The actual features actually are only n-1 dimensional. So in the very first step, we initialize our weight vector simply as 0, right? And then we sequentially go through each training example, xi and yi, right? We first use our current model, which are parameterized by WT, right? We use our current model, WT, to make the prediction, right? So as to get our prediction y prime, right? Then we check if our prediction is the same as the ground truth, which is yi, right? So if yi is equal to y prime, then we do nothing. So this is also called lazy learning, right? We do nothing. Now that our current model can correctly predict the incoming training example, we do nothing. We switch to the next training example. Right? Otherwise, we make some kind of update, meaning that, okay, we only update our model when we make mistakes, right? So how can we update our model? Here is the most important part. So this is a rule, it's called the Perceptron rule. How can we update our model? We add WT to some learning rate R multiplying with yi times xi. So remember, yi is a scalar, right? Either +1 or -1, and xi is an input feature vector, right? We just multiply yi xi, and then a learning rate R, and then add this portion to the current weight vector to get our updated weight vector, WT plus 1. And then we look at the next example and do the same thing again and again until we finish the maximum number of updates, or we haven't seen any examples after going through the whole training set, etc., or any other stopping criteria. And finally, we return the weight vector. Okay. So those are the algorithm details. Any question regarding those whole algorithm framework?
So visually, what does it look like for WT to be added to the scaled and signed vector of xi? So like, what does that kind of look like on a graph?
Yeah, that's a very good question. We're gonna discuss later. But first, I want to ensure everyone is kind of clear about those algorithm steps. Namely, that even I don't understand why we kind of have this similar peculiar updates, I can still implement. Are those algorithm steps sound clear to everybody? Okay, I assume everyone is comfortable with this, right? Okay. So you might see from some other tutorial or textbook, they're gonna use binary labels like yi is either 0 or 1. Right? It doesn't matter, right? Because here, if we want to use 0, 1, we need just to replace the yi here by 2 yi minus 1, right? So if yi its range is either 0 or 1, then you need to replace the yi here in updating rule by 2yi minus 1. Why? Because it maps 0, 1 to -1 and 1. Right? You can check out later, right? It's a very commonly used trick. Okay. So now let us look at why we should conduct such kind of update when we make a mistake, right? So, and also to corresponding to respond to the question someone just asked, right? What is the interpretation? What is rationality of this update, right? Why should we do this, right? We're gonna give both some kind of analytical analytical explanation and also give some geometry interpretation, and you'll see why doing this is reasonable. So before that, we can just take a closer look about this update, right? So first, because when we make in the perceptron algorithm, we only make updates when we make wrong predictions, right? So we have two possible wrong predictions. First, if the ground truth label is positive, meaning that, okay, you're misclassifying a positive example. And then, according to the update rule, right, yi is 1, right? And then your update rule is essentially add wt to this r, constant learning rate, times xi, right? On the other hand, like, suppose you're making a mistake on negative example, namely the ground truth label is negative, while I now becomes a -1, right? So updating rule becomes wt subtracted by r multiplying with xi, right? So we're gonna look at these two cases, right? How those two cases are rational. And here, again, I want to emphasize that R is a learning rate. It is quite similar to the learning rate we have discussed in our stochastic gradient descent and gradient descent, right? It's a small positive number, less than or equal to 1. Right? Although in our theorem, in our analysis, for convenience, we just choose R to be 1, right? But in practice, you can choose R to be sufficiently small to make your update more smoother and more stable. And a third observation for the whole perception is that, okay, this is kind of like mistake-driven algorithm. Why? Because it updates only on error. If your yi is the same as the prediction y prime, we do nothing, right? We just switch to the next example and make prediction and check again. So this is why it's called a mistake-driven algorithm. And finally, it's just a notes. This is the simplest version, and we'll see more robust versions at the end. And one last thing, we should be aware that to check if our prediction is correct or not, we can use this inequality. Right? In other words, we can just check if this inequality holds. Right? If this inequality holds, it means, okay, our current prediction on the training example xiyi is wrong. Otherwise, our prediction is correct. So now I want to ask why. Can anyone take a closer look and give us a hint why we can just use this inequality as our test condition for mistake?
The mistakes will only happen when the signs of y and wt x are opposite, so they'll always be negative.
Yes.
But
yeah, you can supplement more. Yeah, go ahead.
Oh no, it was just negative times negative is always positive. So
yes, exactly right. So a more a more detailed analysis will be like you just consider two cases, right? We will make mistake on positive examples. We'll make mistake on negative example, right? So if we make mistake on positive examples, you know that your ground truth yi will be positive 1, right? But because you're making a mistake, your prediction will be negative 1, which implies that your classification function value will be negative, right? So positive multiplying with a negative value will be negative. Right? On the other side, suppose your ground truth label is negative, right? But you make wrong prediction, meaning that you predict this example xi as positive, meaning that your classification function value is positive, right? So again, -1 multiplying with a positive value will be negative as well, right? In both cases, in both types of mistakes, you're gonna have this product yi wt transpose xi always being negative. That's why we often use this value, this product, to check if our prediction is wrong or correct. And we'll see this kind of this product again when our classes proceed. Okay, now let us look at the intuition behind the update. Right? So we're going to start with the analysis on the positive example. Namely, suppose we have a same incoming positive example x and y, right? But our current model, parameterized by WT, has made a mistake. Namely, the ground truth label is 1, but the classification function, WT transpose x, is negative, right? So we'd like to say, okay, after our update, right? After applying our update rule, if our model can indeed improve in predicting this particular example x and y. So how to check that? We just denote our updated vector, updated weight vector by WT plus 1. Right? Current model is parameterized by WT, right? After one update, we denote our new weight vector by WT plus 1, right? Just copy the updating rule here, right? So, and we simply set R equals to 1, right? The learning rate equals to 1. So we get WT plus 1 by adding WT with X, right? So we want to check with this new weight vector, WT plus 1, is it possible for us to correct the misclassification we made before we do the update? So to check that, we just look at the classification function value using the updated weight vector, WT plus 1, right? We just calculate this new classification function value, right? So now because we know that WT plus 1 is simply WT plus X, right? So we substitute this WT plus X for WT plus 1, right? And then calculate the inner product in the function value, right? So get that, okay, this classification function after the update is equal to the previous classification function plus the inner product between the input X and itself. And we know that the inner product between any input, any vector, and itself is non-negative, right? So that means we're actually increasing the classification function value after performing the update, right? So WT plus 1 transpose X is bigger than WT transpose X. That's our key observation. So now I want to ask, is this improvement reasonable? Or this increase reasonable? So let me summarize again, right? From our analysis, we see that for a positive example, right, the perceptron update will increase the score assigned to the same input. Right? The score is the classification function value, right? So now I want to ask, is the increase of the score reasonable? A good thing or something we are happy to see?
Yeah, because we made a mistake because the value was too small, and so if we're increasing, then we'll get closer to the truth or closer to the right value, right?
Yes, exactly, right? That's where we see the rationality of conducting such kind of update, right? So the reason we make a mistake in predicting these positive examples is right because our prediction score is too small, right? So suppose this is 0, right? Here's our prediction score, right? It's below 0. That's why we make mistake, right? If we want to correct mistake, we want to lift up the prediction score to be bigger than 0, right? Then we can correct our mistake. We can predict a positive example, right? And performing the perceptron update rule can indeed increase our prediction score. So we're more likely to correct our mistake, right? That's why it's good to apply this perceptron update rule, right? But of course, it does not guarantee that by performing only one update, namely updating by adding this x transpose x, it guarantees to lift your prediction score to be above 0. It does not guarantee, but at least it kind of improve the model, right? That's the rationale.
I have another question about this. So we've essentially put our bias term into the W vector.
Yeah.
And so because of that, what that means is that when we, if we're going to, in this case, we're adding X to WT to calculate our new weight vector. So that means X is completely independent of B. So like what it seems like then is WT plus 1 is just going to be like a rotated version of WT, because we're not, I just don't, I mean, maybe I'm seeing this wrong, but it looks like you wouldn't be changing B in this case. You would just be changing the magnitude of the weights on the W vector, which is just going to cause it to rotate.
No, B is changing as well. Remember, WT includes B as well, right? So X actually includes 2 items, right? The original features, let me denote this by X bar, and a constant feature 1, right? And WT actually consists of the true feature weights and the bias parameter B, right?
Oh yeah, okay.
kind of like counterparts to each other.
Right. Okay. Yeah. I was thinking about this a little bit wrong. Okay. I see that now.
Yeah, but anyway, from this general analysis, we can see that the prediction score is indeed increased, right, after this update. Right?
Okay. Right.
Yeah, that's something we want.
Right. Okay. Cool. Thank you.
Yeah, we can apply the same kind of reasoning, right, for the negative examples. I would say we can get the same conclusion as well. Right here, I just I'll give a brief description. Right, I would like you guys to perform same kind of reasoning after the class. Right, so suppose we made a mistake on negative example, meaning that our ground truth label is -1. Right, however, we incorrectly predict this example as positive, namely the prediction score is positive. In this case, the source of our error or the reason of our error comes from the fact our prediction score is too large, right? So it's supposed to be below 0, right? However, this is where our prediction score stays, right? We want to decrease the score to correct our mistake, right? And then we can analyze if our update rule can help us to achieve this goal, right? So, and in the negative case, right, our new weight vector is actually obtained by subtracting WT by X, right? This is just following this rule, right? So R, again, is set to 1. So we'll subtract WT by X, and we'll calculate new prediction score. Remember, the plus sign here is replaced by minus. So again, this plus sign replaced by -1. So you can see that our prediction score, new prediction score, is old prediction score subtracted by this inner product. Again, because this inner product is always non-negative, right? So our new prediction score is actually decreased, right? So they actually consistent with our expected change of the prediction score after the update, right? Because we made a mistake because because our original prediction score, the previous prediction score, is too large. Now, performing some perception update, we kind of decrease the prediction score. So we're making efforts toward the right direction to improve our model, right? Of course, if after only one prediction, we can decrease our prediction score to be below 0, then we can totally correct our mistake, right? But it's not guaranteed practice. At least, I mean, such kind of update is kind of, obeys our expectation of model improvement. Okay, any questions so far? Great. So to give a more, better understanding and view of this perception update, we'd like to illustrate the geometry, the change of the geometry after perception update, so that everybody can have an even better look, a nicer look. So suppose this is our current weight vector, right? We just denote the weight vector by WO. Remember, this is our classification boundary, right? And WO, the weight vector, is always orthogonal to the classification boundary, right? So now, suppose we say a positive example. So X is represented by this black vector, right? Its label is +1, right? So now, if we use current weight vector to predict the label of X, what is the prediction?
-1.
Why?
Because it's on the dot product between X and W old is going to be negative.
Why is it going to be negative?
Because the angle between the two is greater than 90 degrees.
Yes, exactly right. I just want to, stimulate your, or just to let you guys to think about, to memorize that some kind of like common sense in our high school math or calculus, whatever, right? So we know that two vectors, their inner product, the sum of the inner product is determined by the angle between them, right? So if the angle is right 90 degree, their inner product is simply 0, right? If their angle is bigger than 90 degree, then their inner product will be negative, right? Otherwise, if the angle is kind of small, right, is less than 90 degree, their inner product will be positive, right? So obviously, the angle between WO and this input vector X is bigger than 90 degree. So their inner product is negative. We're gonna classify this example as negative example. Obviously, this is a misclassification, right? So now, because we made a mistake on a positive example, right, we're gonna use this rule to update our weight vector, right? So again, we take R equals to 1, right? So we're gonna add this current weight vector to the current W to get its updated version, right? So we're gonna add W and X, right? How can we perform it in geometry? We just do some parallel moving, right? We just move X in parallel such that we ensure the starting point of X coincides with the ending point of W, right? And then I will just connect the starting point of W and the ending point of X. Then we get our addition result, right? This is how this is the rule of adding two vectors in geometry, right? So in this way, we get our new weight vector, right? And meanwhile, because the classification boundary is perpendicular to the weight vector, we get our weight vector, right? You see that actually the hyperplane is adjusted according to the weight vector, right? So now, what is the prediction of this positive example X with W new? Any hint? Or is this too simple? Again, we just look at the angle between our weight vector and the input example, right? I say, okay, thanks, Spencer. So you see that obviously the angle is less than 90 degrees. So it is positive, meaning that the prediction score is positive. Now, after the update, we can correctly predict X to be positive, right? So in this particular case, we show that, okay, after one perceptron update, we have already been able to correctly predict the positive example, right? Obviously, it's just to showcase the effect of perceptron update. In practice, it might not be guaranteed, right? Just using one update can correct a mistake, but you can do it multiple times, right? When we go through the whole data set, multiple passes. Right? So this is the illustration for the perceptron update on a positive example, right? Let us look at the case of negative example, right? So again, suppose this is our current weight vector, right? Obviously, this is the classification boundary, right? This is WO. And now, suppose we have saying a negative example X here, right? X is again is represented by this black vector, but its label is negative. According to our classification rule, right, we know that the inner product between WO and X it will be positive, right? Then we're gonna predict X as positive. So obviously, we made a mistake on a negative example. And then according to the rule, right, to perceptron updating rule, we're gonna update the W by subtracting W by X. Right? This is not not adding, it's just subtracting W by X, right? And R constant, the learning rate R is set to 1. And then let us do it in a geometry space, right? So this is W, right? So to subtract W by X, right, to calculate the difference, to show their difference, we're gonna first invert the direction of X, right? So first to construct negative X, which is just to switch the starting and ending point, right? And then we just do the things like vector addition, right? So just move this negative X, negative X is along this direction, right? The opposite direction to X. We just move negative X in parallel such that the starting point of negative X overlaps with the ending point of the weight vector W, right? And then we just, this is essential to saying that we add W and minus X, right? And then the addition results is simply connecting the starting point of W and ending point of X. Forgive my, this bad drawing, right? So this is actually the result vector, right? So now we get our new weight vector, W new, right? And accordingly, we adjust our classification hyperplane in this way, right? So now, what is the prediction result using W new to predict X? It's negative, right? We just look at their angle, right? The angle between them is obviously bigger than 90 degrees. So the classification function value will be negative. So we correct our mistake. Okay, so any question regarding the geometry interpretation about the perceptions? Is everyone on the same page? Feel comfortable with that? Okay, yeah. Hopefully, through this kind of like a relatively detailed and even tedious, lengthy analysis can give you a good understanding of the perceptron algorithm steps, because it's really important. Right? When you implement this algorithm, you really need to know what's the rationality behind every step. Okay, what is the learnability of perceptron? obviously perceptron cannot learn what it cannot represent, right? So perceptron is only for learning a linear classifier, meaning that it can only learn linearly separable functions, right? If the data set or if your target function is not linear separable, of course perceptron cannot learn. And when we discussed the expressiveness of linear classifiers, we mentioned that even for a particular type of the balloon functions, like parity functions, we cannot find equivalent linear classifiers, right? So a typical example is XOR function. XOR function is a function of two balloon variables, right? The XOR is 1 if and only if the values of these two balloon inputs are different, right? X1 is 1, X2 is 0, or X1 is 0, X2 is 1, right? In such a case, you'll find that no matter how you draw a line, right? How you draw a line, you can never separate all the positive examples from negative examples. So all those problems, right, about limitation of linear classifiers are summarized in this famous book written by Minsky and Pepper. They're a pioneer in artificial intelligence. Minsky passed away several years ago. Yeah, just passed away, right? Several years ago. And they wrote an influential book demonstrating the perception's representation limitations. So actually, they wrote this book is just to point out the issue of perception, right? It's not as so fascinating and so powerful as claimed or hyped in newspapers and in all kinds of media. It actually is so simple that it even cannot classify XOR function, and this directly brings the artificial intelligence into the winter. But nowadays we know that the linear classifiers, right, in their original feature space, they indeed cannot classify parity functions, right? But by applying some feature transformation trick, right, when we transform the inputs in the original space to some higher dimensional space, you can still find a linear classifier which can separate positive and negative labels given by parity functions, right? So if you are doing the homework too right now, I assume that you have already got some cool idea to perform such kind of feature transformation. Okay, so now we have introduced the details of the perceptron algorithm. This is just the standard framework of perceptron algorithm and serves as the core and the foundation when we introduce the more complex version of perceptron. So any questions so far? Is everyone good? Okay, great. So now let us talk about a little bit theorem. It's not hard at all, but it is very helpful for us to understand the nature and behavior of the perceptron algorithm. So this theorem is called perceptron mystic bound, namely how many updates at most can perceptron learn to update model. So so before that, I would like to first briefly introduce two theorems which characterize the behaviors of perceptron. So the first one is called the convergence theorem. So what about convergence theorem? It just says, okay, if your data are indeed linearly separable, meaning that I can always find, there indeed exists a set of weights and bias parameters such that using them to construct linear classifier, you can perfectly separate all the positive examples from negative examples. Then when you apply the perceptron algorithm on such a data set, your algorithm will always converge, right? Namely, it can always find a separating hyperplane which separate a linearly separable data. That's a good thing, right? It's just saying, okay, as long as your data is good, right, the perceptron algorithm won't have any problem to find you a separating hyperplane. But what if the data is not linearly separable? And then the perceptron algorithm cannot converge. It will enter an infinite loop. Right? So this is called cycling theorem. If the training data is not linearly separable, then the learning algorithm will eventually repeat the same set of weights again, right? Unless you intentionally stop running the perceptron. So imagine that you might have suppose your data is not linearly separable, meaning that there's not any hyperplane which can separate positive examples from negative examples. Then if you keep running your perceptron algorithm, you'll eventually enter into a state where you're gonna just cyclically going through like 8 distinct weight vectors or 10 distinct weight vectors, then forever and ever. So these are the two behaviors of the perceptron algorithm. Right? Under linearly separable data, perceptron algorithm guarantees to find a separating hyperplane. Otherwise, it cannot converge until you intentionally stop it. Okay? Any question? Okay. So now we'll be interested in the ideal case where the data set is linearly separable. Right? So under the linearly separable case, we know that, okay, the perceptron algorithm eventually will converge and give you some linear classifier which perfectly separates positive examples and negative examples, right? But how many updates will our perceptron algorithm need to find such a hyperplane? In other words, how many mistakes the perceptron algorithm has to make before it finds such a separating hyperplane. This is something we're going to discuss in detail. So to illustrate, to find such a upper bound of a mistake made by the perceptron algorithm before convergence, we need to introduce a very, very important concept. It's called margin. So we're not going to use the concept of margin to construct some kind of mystic bound or update bound for perceptron algorithm. We're also going to use that to illustrate more advanced linear classifier learning algorithm in support vector machines. So what is margin? So the margin is originally used to define the property of a separating hyperplane. So we say if a data set is linearly separable, and also we have such a separating hyperplane, then this hyperplane has a margin. And this margin is defined as the distance between the hyperplane and the data point nearest to it. In other words, it's the minimum distance between the data points in the data set and the hyperplane. So to give an example, right, this data set, positive and negative examples, right, obviously they are linearly separable, and we have already found a separating hyperplane. Right? And what is this margin? We just calculate distance between every data point and this hyperplane, and use the smallest one, the smallest distance, as the margin of this hyperplane. Right? So the smallest distance obviously comes from the distance of the nearest data point, which is this positive example, right? So its distance to this hyperplane is the margin. So you can see that not all data set and not all hyperplanes have a margin, right? Only when we have a hyperplane that can perfectly separate the positive and negative examples, it has a margin. Right? If the hyperplane cannot well separate the positive and negative examples, it doesn't have a margin. So now comes a question, right? What if some example or some data points stay right on the hyperplane? Say, suppose there is a positive example here, right? So what is the margin? Yeah, thanks. Thanks, G-Rod. Thanks. Yeah, it's 0, right? Because it's just the distance between the data point nearest to it. If the point stays right on the margin, the nearest distance is 0, right? Distance is always non-negative, right? Okay, so so the original concept of margin is a property of a particular separating hyperplane for a data set, right? So we can generalize this concept to be the margin for a particular data set. So if a data set is linearly separable, and we just take a look at all possible separating hyperplanes, and then we use the margin, the hyperplane who has the largest margin as the margin for the whole data set. So take this particular data set again as an example, right? So we know that this data set can be separated by many different hyperplanes, right? So obviously different separating hyperplane will have different margin, right? Like this dashed blue line, right? The margin is quite small, right? Because it's very close to this particular positive example, right? And this dashed black line, its margin is much bigger because distance between this positive example and this hyperplane is much bigger, right? However, only this solid blue line has the largest margin because if you calculate the minimum distance between examples in the data set and this hyperplane, this minimum distance is bigger than the minimum distance for any other separating hyperplane. So we use the margin, the largest margin of the separating hyperplane as the margin of the whole data set. Okay? So what does this mean, right? So the margin for data set actually reflects some property of the data set. Can anyone think of it, right? What kind of property or what kind of nature does the margin of the data set reflect?
Perhaps some level of certainty about like how easy it is to categorize things in the data set.
Yes, exactly, right? Hit point, right? Yeah, so you can imagine the larger the margin, the easier the data set to be separated, right? So you can imagine if the positive examples, negative examples are kind of very far apart, right? So you can imagine the margin of the whole data set could be very big, right? On the contrary, if the positive examples, negative examples are quite close to each other, say if the negative examples are around here, right? So you can imagine we can draw all kinds of separating hyperplane, right? And pick up the largest margin of those hyperplanes. The margin for the whole data set will be much smaller. So actually, the margin of the data set reflects the easiness to separate the data, right? Or the data separability, right? So we're gonna use that data, right? You see that the margin and those kind of concepts are used in computational learning theory to represent how the difficulty of some classification function or difficulty of the target function and the data set, etc. Okay, and this is one important concept called margin, right? And also, we need to review how to calculate distance. So here I just copy the formula. I bet everyone has seen this before, right? In your calculus course or geometry in high school, whichever, right? So suppose we have a general hyperplane, right, which is in this form, right? W transpose X plus B, right? And we want to calculate distance between arbitrary point x0 and this hyperplane. So this is a formula to calculate distance, right? So how to derive this formula? I will leave it as exercise for you guys, right? You must have learned this before, right? You can try to rederive by yourself, practice calculus, or you just open the textbook and review, right? It's a good thing. So basically, distance is calculated by first evaluate the left-hand side of this equation, right? And then take the absolute value, right, at x0. W transpose x0 plus b, you take absolute value, and then you divide this value by the norm of W, right? Norm is calculated as the Euclidean norm, right? Just the square root of the summation, square root of the summation of the square, sum of the square of each element in W, right? So this is a general formula to calculate distance for a general representation of hyperplane. But when we use this formula to analyze our case, we should be aware that, as we mentioned before, right, we use the augmented feature space. Namely, our weight vector includes an actual bias parameter B, and the input vector consists of a constant feature 1, right? So our general hyperplane is represented by W transpose x0, right? So B is B doesn't show up in this hyperplane representation. This is in the augmented feature space. And then when we apply this general formula to calculate the distance between arbitrary point in the augmented space and this hyperplane, the formula becomes this. And remember, in augmented feature space, x0 includes an actual constant feature 1. So the distance is now the inner product between W and x0, and take the absolute value, and then divide it by the norm of W. And if we have a separating hyperplane, namely this H, or no, we should talk about augmented feature space. This separating hyperplane in the augmented feature space can well separate the positive examples from negative examples. Then we know that it can correctly predict every example, right? So then we can replace the numerator in the distance calculation by this product, y0, W transpose x0. Why? Any thought? Remember previously we mentioned, right? We can use an inequality to examine if our prediction is correct, right? If W incorrectly predicts x0, then this product will be negative, right? We consider two cases, right? When we make wrong prediction for positive example, when we make wrong prediction for negative example, in both cases, this product is negative, right? But here, when we talk about an opposite situation where our weight vector can correctly predict any example, right? That means this product is always positive, right? So since it's always positive, we can just replace the absolute value of this W transpose X0 by this one, right? Because Y0 is either 1 or -1, doesn't matter. Doesn't change the magnitude, right? And for convenience, we can further divide W by its norm. That means after normalization, W becomes a unit vector. Then the distance is simply this product. Any questions so far? So everybody's comfortable?
I have one question about this last statement.
Uh-huh.
So you're saying in this case on the right side of the blue arrow, W in that case needs to be a unit vector.
Yeah,
Because
yeah.
then
If W has already been normalized as a unit vector, then your distance is simply this.
Right, because then if we go back to the equation on the left, the norm of W is 1. So that,
Yes.
and then essentially by taking Y0 and multiplying it by this inner product, that's going to be a positive value. And so that's essentially accounting for this absolute value in the numerator.
Exactly.
Right. Okay.
Exactly.
Cool.
Any other question? Okay, great. So let me spend like 2 minutes to just read through this mystic bound theorem. We're gonna go thoroughly go through it in our next lecture. Right? So what is mystic bound theorem? It just tells you what is the upper bound of a perceptron make updates, the number of updates or number of mistakes made before it converges. So suppose we have m training examples x1, y1 to xm, ym, right? Where each feature vector xi in the n-dimensional space, again, xi is augmented feature vector. It always includes a constant feature 1. Right? And we assume that the length of each input vector is upper bounded by r. So this is the upper bound of the length or upper bound of the Euclidean norm, right? And each label is either -1, 1. And we assume this data is linearly separable, right? This is the major case where we're concerned about, right? We're not interested in the case where the data set is not linearly separable. And suppose this data set is linearly separable, and then suppose there is a unit vector u, right? So we're connecting back to what we discussed about distance, right? So suppose we have a separating hyperplane, which can be represented by this unit vector u, right? Such that there exists some positive value gamma. We have the distance between every point and this separating hyperplane is no less than gamma. This is basically saying the lower bound of the distance between every training data point and the separating hyperplane, which is gamma. So gamma essentially is the margin, right? And then given these two conditions, right? One is about the span of the training examples. The other is about the data set, the linearly separability of the data set. We can conclude that the perceptron algorithm will make at most r over gamma square mistakes on the training sequence. And then it will not make any mistakes in prediction the incoming training examples, and it will return you a linearly separating hyperplane. But this hyperplane is not necessarily the same as u. Okay. So in the next lecture on Thursday, we're going to take a close look of mystic bound, and we're going to show how to prove this mystic bound and explain what kind of insights it reflects. Thanks, everybody. See you on Thursday.